Hello and welcome to ThetaWave podcast. I'm one of your co-hosts, Jacob Holland. I'm a neuroscience enthusiast, and I'm here with my co-host, Ryan Reed, who is an AI machine learning expert and entrepreneur. All right, Ryan, what are we going to be talking about today?
Well, we have a couple things kind of on the docket, but as per the usual, chances are we will not stick to that docket.
We're going to free flow a whole lot.
Yep. And one of the things that we want to start doing with every podcast from here on out, as we kind of feel like we've refined things a little more, we want to start going over a research paper. Every week when we do our podcast on Tuesday, we want to pick up a research paper, kind of delve into some of the details, some of the things that make it interesting, and unique. And so yeah, that's what we're going to be starting with today. Give me 1 second here. We're still working out some of our technical details.
And while he does that real quick, I'll go into a little bit of an overview of what the research paper is going to be.
I'm actually good to continue.
You got it?
So we're good.
Right. So
we are going to be going over J147.
Ooh, what is that? That's a lot of numbers and letters.
That is.
What could that mean?
Well, that's only one letter, but it is a lot of numbers.
Well, we're going to be talking about a lot of letters.
So
there's a lot of letters involved.
Yeah, we've got on J1047. This is a new. Well, not really. It is.
It's pretty new.
It's not. It's kind of a novel new research drug that is being currently looked at for its potential in treating things like Alzheimer's, and that's kind of where its research is focused right now. But it is, as we'll see once we kind of delve into it, it goes beyond just Alzheimer's as a potential benefits.
It's got a lot of benefits, even just for the average person, especially for the average person.
And then from there, we may delve into some neuroscience topics. Both of us have been doing a little bit of research into long-term potentiation. So
neuroplasticity.
We may decide to talk about that, especially since it's really related to J147.
Very relevant.
And we might go from there to, at some point, we may even discuss quantum computing and qubits, since there was some recent development that happened in quantum computing.
See, I actually have a lot of questions about quantum computing, so that would be wonderful. So, we can both learn together from this expert over here.
Well, no, good. I'm not an expert in quantum computing. I don't want anybody.
Yeah, you actually got a PhD in quantum computing, guys.
Understanding that I am an expert in quantum computing, because I actually until recently didn't even take an interest in learning about quantum computing because it had no relevance to my life.
No, that makes sense.
To me, I can only store a finite number of things like up here, and it makes sense to store things that are going to be useful. And quantum computing is not something, knowing how all that works, especially given its complicated nature.
It's insanely complicated.
If it comes to like knowing neuroscience more completely versus quantum computing, I'm going to choose neuroscience because it's way more relevant,
Oh, yeah, 100%.
But I did do a good amount of research into quantum computing recently because I wanted to understand more about this development and kind of
where it's going to lead us in the future.
Right. The guy that was explaining it was the guy that was in charge of the entire quantum hardware division at Google. And so he, as you can imagine, with something that niche and technical, he wasn't very good at explaining himself.
Yeah.
So it kind of spurned my, okay, I'm feeling like I'm somehow behind the times here and like not up to
Hey, you're an
speed.
old timer, bro.
And so I need to like go into research mode and figure this out. And
I'm sure they didn't hire him because of his communication skills, but more so his IQ and ability to understand something and lead a team of people to understand quantum computing, which I have no idea about. I'm still trying to grasp the basics of quantum mechanics, so I can't even imagine what quantum computing is like on that level,
It's actually super, super fascinating. And without delving
too much, we got to go into our research.
We got to go into our research papers first, but I do want to say that we are still refining. This is still a beta episode.
Yes.
The last episode that we launched looked great, but didn't have any sound whatsoever.
Zero sound.
And
it sucks because it was like a 2-hour podcast, just completely just useless, wasted, which sucks. But that also means we can,
reuse
some of that content and talk about it. Maybe not in this podcast, but in the future, because it was very interesting.
Once you and I forget that we talked about it.
Yeah, exactly. Because what did we talk about? It was like a lot of different types of government and different of that sorts. And
that's true. Yeah, no, we did talk a lot about. It wasn't even on topic for our podcast.
No. We kind of just got into it like we're doing now. We're going off topic, but
so
we're gonna free flow.
To make sure that doesn't happen again, I've done it. I put it in several checks in place. I need to. A further refinement I would like to make is turning off this screensaver that keeps on popping up here.
His screen keeps turning off. Yeah, but we still got video. We're chilling.
Mm-hmm. Okay.
Bear with us.
So, one thing that I would like to do real fast that will not happen every podcast, but I want to make sure, and to ensure that we don't waste 2 hours here, we are getting audio through, right?
Yes.
This time,
gotta make
because
sure
of the last time. So we are going to. We'll let you. You're
going to listen to the podcast that you're watching on the podcast. We got audio.
We're getting some audio.
Nice.
Good deal.
All right. All the technical problems are fixed.
I feel a little safer here proceeding. And let's see if we can turn off this screensaver real fast.
Now, one thing about
go ahead. Yeah, go ahead.
Oh, as you're doing that, I was just gonna say, one of the books that I've really wanted to start reading that's like a comprehensive overview of quantum mechanics is Something Deeply Hidden by Sean Carroll. I used to have that book actually in like 4 years ago, before I even got into this stuff. We had that book and I read the first chapter and I was like, what the heck even is this? But now I can't find the book, so I think I'm just going to get it again. And then hopefully that'll give me a good overview of what quantum mechanics is, because that guy does a wonderful job at communicating at least the basics and a comprehensive overview that everyone can understand. So if you're interested in quantum mechanics, I think I would recommend Something Deeply Hidden by Sean Carroll, because I love listening to that guy on a podcast because he's able to explain things very precise, eloquently, and simple for the average person, which I think is really awesome. I think it's really cool. But
so, speaking of that, the last night I spent a long time with the quantum mechanics topics that I was researching, trying to understand them enough that I could create an accurate analogy to make some of these really, really difficult principles a little easier.
Yeah. Did you come up with anything interesting?
And I did. I came up with something that was actually surprisingly accurate as far as analogies go, especially given that we're talking about something like quantum mechanics.
Yeah, which is in nature very positioned to have many errors in conceptualization. because it's been used a lot to have some nice woo-woo cults based off of it, I will say. And I've listened to some of their books, and I'm like, wow, that's nothing like quantum mechanics is. Very fascinating.
Mm-hmm. So let's see here.
My favorite one was Quantum Faith, which was how the biblical teachings of Jesus are speaking of quantum mechanics. About quantum mechanics is what they say, is that Jesus was teaching quantum mechanics. Which, that guy had some great stuff to say, I will say. But not quantum mechanics.
Hope I dealt with it. I'm not 100% sure that I did. But, oh well.
Yeah, did you know the Sermon on the Mount was actually about the particle wave duality?
Whoa, wait, what?
I'm just kidding. I just made that up. I don't think that's even in the book.
How do we get back to where we were here? There we go. All right, thank you for bearing with us there. I hope I killed that screensaver. I don't want to see it ever again.
Let's get into this nice new experimental drug called J147.
So J147 was one of those that when I first started reading, it seemed like it was a kind of like every other research chemical that I've been interested in, which is primarily taken the form of the ones that stimulate neurogenesis, because that's something that really fascinates me, and especially given that typically neurogenesis declines
over age
as we get older. And as a result, you end up with not only a more limited cognitive capacity potential, but you also end up with the inability for the brain to rewire itself given the degradation of its older neurons. So that's been something that I've always taken kind of a special interest in the research chemicals, compounds, the things that are being developed that show that potential. And so this one for me kind of started off as I was looking into it, looking like it was another one of those.
It's like, it's going to have some nice, maybe interesting effects, but not necessarily anything like groundbreaking.
Right. And a lot of those are developed primarily for Alzheimer's and Parkinson's and other diseases that are caused by degradation of neural pathways and a degradation of the neurons in some form or fashion. Like Alzheimer's, a lot of it has to do with the neurons that not only hippocampus, but the connection between the rest of the brain and the hippocampus. And, with Parkinson's, a lot of that has to do with dopamine neurons, to my understanding. And so that's kind of a lot of the motivation behind the research on these, which is why a lot of them mention Alzheimer's applications, Parkinson's applications and whatnot. But that doesn't mean that's their only use case. So this one first kind of addresses it in a lot of its initial papers. It first addresses its application to Alzheimer's disease, which I think, I do think if they could find a way to consistently solve would be amazing.
100%.
I know several people that have had relatives that have been affected by Alzheimer's or that have been personally affected by Alzheimer's. And so this particular one is interesting, as you were saying, Jacob, because its molecular formula was based off of
Turmeric.
Yeah, exactly. And what do we know about turmeric? Turmeric is a potent antioxidant. Turmeric is neuroprotective, and has shown some potential neurogenerative properties. So it makes sense why they would look at that molecule for, to base kind of some of their potentials off of.
Yeah, there was this book by this guy who calls himself the Brain Grain Doctor. And interesting name, but pretty much he just in his books said, listen, if you want to keep a nice and happy, healthy life, add turmeric to every single one of your meals. And, when my mom first told me that, I was like, oh, that's a very interesting idea. Like, sure, it has some great properties. I'm sure that, has some actual implications for our daily lives. And as it turns out, it really does. And you can actually enhance it to a large degree with, changing its molecular structure slightly, like these guys have done. And to emphasize this is still still preclinical testing. I think they're just starting clinical tests. So we do not recommend trying this, but rather we are just seeing its potential for this stuff. And we just have to emphasize that this is not anything that we are saying you should take or anything of that sort. Just saying, okay, this is what the studies have shown recently and what it could be for. So yeah, anyways.
Exactly. Yeah, no, that's a really good point. We're going over research here because it's fascinating and it applies to the potential future for these areas. And so I think what ultimately I'm of the opinion what you do is not my business. Just like, what we do, it's not anybody else's business. And so we're not encouraging, to
take any of
try this stuff. But in my opinion, the best decisions are the informed decisions. So that's all we're going to say about that. Go ahead.
I was going to say, this might make us want to take it, but that doesn't mean you should at all. You can just watch us take it. And
what is that? What is that thing that people used to say on Reddit, where they were wanting to post something about asking about something they didn't want to admit that they wanted to know about, and so they would say swim wants this, or swim wants to know, and it stood for someone who is not me.
Oh, nice. Yes, that is this right now. Swim wants to take this stuff, and we are going to see if Swim has it right and if they really should. So yeah.
So we're going to quickly, before we delve into this paper, we are going to quickly take a short break. I know we just started, but this screensaver is disrupting my video feed. So that's why I've been kind of a little distracted while I've been looking at stuff, because I've been trying to figure out what's going on here. So before we delve into this really exciting research paper, I want to quickly transition us just for a brief moment so I can figure out the screensaver issue. And we'll see you guys in about 3 minutes or so.
3 minutes. All right, guys.
All right,
We're
are
back.
back.
Indeed. All right.
We are indeed back.
Now?
I think I've resolved the issue, and we should
to go.
be good to go. Okay,
So-
so
J147.
yes, J147.
Tell us about it.
Let's delve into this. Well, you read the research too. I
Mhm.
sent that to you.
Yes, which I found very fascinating.
So some of the key highlights here. I'm just going to kind of go over. I wrote some notes down on the research, and it's got some pretty interesting stuff. We'll quickly go over the effects that they have noticed. Now, keep in mind that this research, a lot of it is with in vitro or in vivo studies, and because they're just now starting the preclinical. I think
they're about to start
the preclinical.
I think what is preclinical like?
Animals? Preclinical is. Are you kidding me? It's still turning off the screen.
That's interesting.
Yeah, they're just starting preclinical studies, and preclinical versus clinical. Preclinical is, I think, when they. I looked up at one point. It's. I think preclinical is when they do it's either when they do a small. I think it's when they do a small test study first to see if there's any adverse reactions.
Before it goes to like the masses.
Right. And then a clinical study is a much larger study.
Okay. That makes sense.
And real fast, before we go into that, I'm going to switch us back to our waiting screen.
Yes.
And we are going to resolve this issue because I don't want my camera to freeze on you.
Sorry about this, guys.
Again, we're fleshing out.
Stay with us.
The rough spots here. So thanks for being patient.
If you're watching this after it's uploaded, then all you can do is just skip over this part.
Or you can just wait for our edited version, which will have all this stuff out.
Exactly. Probably even this conversation.
And we're back.
We're back. Oh, yeah.
Okay.
Okay.
You're still going?
Never mind, we're chilling.
Okay. Alrighty. So I set my screensaver to 1,000 minutes. So hopefully, we have some time before that goes off.
So we talked about how J147 improves cognition. How does it do that? I'm actually very curious.
Yeah.
about the
So
specifics.
This has always been something that has interested me because, and by this, I'll explain what I mean in a second. Cognition is a somewhat ambiguous term.
Yeah, like what does that actually entail? There's a lot of cognitive functions.
Right. And I think rarely does something just overall improve
the entirety of
every aspect of cognition.
I mean, if it did, that'd be pretty cool.
Right.
Well,
so I do think we kind of use that term a little too liberally. But we'll get into the how in a second.
Okay.
Just kind of want to go over a brief overview of like the effects and whatnot that they noticed in these studies. I actually have another one lined up for next week too. That's kind of similar to this one.
Okay, perfect.
Yeah. That one actually has gone through preclinical trials.
So this is going to be a part of our daily lives, maybe sometime sooner than this one.
Anyway, so one of the first effects that they noticed was that it consistently improved cognitive function. So the various areas of cognitive function we will try and delve into a little bit more with the section that goes over kind of the mechanisms of action here. But I do want to point out that a lot of that stuff, the complete effects and the way that it interacts with the brain are not known a lot of times because there is not enough data and not enough studies that have been done on it to be able to gather that kind of detailed information. And so that's likely why terms like cognition are used in general. It's a way of encompassing just an improved cognitive, a noticeably improved like cognitive performance in specific tasks. So while they'll probably go over the tasks that were performed, and that can be used to kind of gauge the certain elements.
So would you say increase
certain elements of improvement? It's not necessarily limited to those elements.
Yes. So it's as if it's increasing the speed of plastic connections within the specific task, not necessarily specific tasks in and of it themselves. Is that what you're saying?
No,
so like
I'm just saying that our observations of it are limited to the tasks that we perform and notice an improvement in.
I see.
That doesn't necessarily mean the improvements are limited to those areas.
So they could be in other areas
as
well.
More expansive than that. Yeah, exactly.
And I would guess, I mean, especially with what we know how plasticity works, you know, it would be an overall encompassing cognitive performance specific to the relevant tasks for your cognition to handle, you know? So that makes sense.
All right. So moving on to the second one, it was, they noticed that it had neuroprotective qualities, specifically that it protected neurons from damage and even death.
Interesting.
And
the death of the cells.
And specifically because of the focus of this research, they were looking at its ability to protect from these highly ravaging things like Alzheimer's and whatnot.
Is that because of its usage and increasing in ATP levels?
We'll get into that
Okay.
once we finish going over the effects. But it reduces the oxidative stresses in the neurons, as well as inflammation. And inflammation is a huge cause of almost every many brain-related issues are caused or worsened through inflammation. So it also reduced excitotoxicity. So that's kind of the areas.
Can you explain a little bit more what excitotoxicity is, perhaps?
I don't know if I could explain it in a easy to understand and quick way. I haven't even thought through trying to explain that to anyone, but we might have to do another.
From what I can see, excitotoxicity is when nerve cells or neurons in the brain become damaged or die because they're overstimulated by too many brain chemicals, by like too many of the certain brain chemicals, particularly glutamate.
Yeah, that is actually a really good. Actually, that's how I should have put it. My issue was, it's not really an easy question to answer because excitotoxicity can happen for a number of reasons through a number of different pathways. Such as like you can get again, this is to my understanding, you can get excitotoxicity from dopamine overusage, and that can lead to issues like lack of motivation and things like that. There's these even I have experienced some of these effects over the course of my life, but like there's a specific term for what, and I'm blanking on what it is right now, which is I'm struggling with this, but that happens when you have dopamine caused excitotoxicity. I can't remember what it was, but the effects of which are basically like lack of energy, lack of motivation.
So it's like the overloading of the electrical circuits until it burns out, pretty much. Then it has to either regroup or die, pretty much.
Sometimes it can even damage the neurons beyond repair, almost like. So we can imagine excitotoxicity kind of like overusing tiny little CPUs and heating them up and not doing anything to manage that.
So they just keep getting hotter and hotter and hotter.
That heat. And so what happens eventually, you start seeing reduced performance. You start seeing it struggle with like very, very basic things. It might not work the way that it was, that it was intended, until eventually, the likely scenario is that is going to pretty much die. And you're not going to be able to use it anymore. And
that takes more energy to clean it up as well.
Right.
Yeah.
And that's kind of the analogy that I was searching for. But so
it's very important that excitotoxicity is not a part of our daily lives.
Right.
Yeah.
Well, I feel like our culture does struggle more now with excitotoxicity than it has in the past. And
could that be a result of social media?
I'm sure that helps. Hurts, but
helps excitotoxicity.
That contributes to excitotoxicity. I don't know if that is the primary.
Probably not.
Determining element there.
There's a lot of factors in play.
Yeah, and a lot of things that can contribute, including genetics and whatnot. So
that is
anyway.
interesting. Yes.
Going on to the next benefit, they also noticed that it increases the neurotrophic factor and neurotrophic activity. So BDNF and NGF specifically were ones that they noticed, and those are ones that are central for neuron growth and survival and the creation of new connections and that kind of stuff.
Okay. And is that mainly within the dentate gyrus of the hippocampus, attributed to neurogenesis? Is that a part of that, or is it extended beyond to more brain regions as well?
They didn't say.
They didn't say.
My understanding is that the neurogenesis, usually the large majority of neurogenesis will happen within the hippocampus. I don't think it is exclusively limited to that. There are other, it does happen in other areas of brains, but it's just like the gradient is much more weighted.
I mean, it makes sense, right?
Towards the hippocampus and the other areas of the brain that is different, is going to be different. Its ability to stimulate neurogenesis is going to be different than its ability to create new connections. So that also kind of bias or weight would be different from its ability.
So this is kind of more contributed to overall cognitive functionality in that sense, you could say.
Yeah.
Okay.
So the next one is that they noticed a disease modification element to it, where the J147 and the animal models of Alzheimer's and whatnot, J147 showed potential to actually not only slow down and halt, but even reverse the changes that were attempting to be made by the Alzheimer's disease.
Okay.
And so it was actually able to undo some of the damage that was caused there.
Fascinating.
Yeah. And then one of my favorite elements, and this is kind of the one that really caught my eye when I was looking into this, because there's other ones that have shown benefit for slowing down Alzheimer's and progression, and for neuroprotection and neurogenesis and creating new axon connections within the brain, new axon sites and whatnot. But this is the first time I've ever seen this particular one in a
reversing the effects.
Well, but that's actually not what I was referring to. That is true, but I didn't notice that at first. That wasn't the thing that caught my eye, that kind of made me notice it. It was this next point here, which was that they noticed, and this was a different study that was done on J147, but they noticed in a study with fruit flies that J147 has the ability to extend a lifespan. It shows anti-aging effects, and not only that, but the ability to reverse the degradation caused by aging. And now, I'm not saying this is a miracle drug that's going to just cure aging, but the fact that this exists, it's kind of like a proof of concept, almost. We've at least many of us have suspected for years that the human aging condition is not something that is necessarily necessary.
Yes.
And that's, as it would follow, given the right resources and information, human death is not something that is absolutely necessary. And this is almost, to me, is almost a proof of concept of this. If a cell can have its aging reversed and can be restored back to its optimal state, then in concept, again, provided environmental factors such as you getting hit by a car, or disease factors, this shows that the death caused by aging is not something that is necessarily necessary.
See, the evolutionary biologist in me is so fascinated by this, because what J147 pretty much does, or what it shows in the study, is that it actually, so very interesting. It actually can, so as we age, the transcriptomes in our cells, the genetic material, correlated with like mRNA, J147 actually will keep the genetic code in place in the cells to keep it in its functional state according to the genetic code that is within the cell. And let's say in fruit flies, it extends a lifespan beyond a certain point, and we keep doing this with the offsprings of these cells, or the cells of the flies. As this keeps progressing, the genetic material of J147 starts to be encoded within the organism itself, which then propagates a pretty much new organism at that point, because now this fruit fly, maybe instead of being alive for 2 or 3 days, is now alive for a month or a year. And what are the implications that would have on its informative experience?
I don't want fruit flies living for a year.
Well, they could evolve into something completely different than fruit flies at an exponential rate with, interference from, this drug that could completely change the code of the cells within the housefly.
An interesting question, like, given if we had the ability to extend the human lifespan, not even indefinitely, but just significantly, how would that affect the human evolution process?
That would be interesting. Like, imagine you're 138 and you're still at peak performance cognitive ability with neuroplasticity happening.
Ability to learn new things, create new neurons, new connection. Dude, some of the smartest people in the world would be the oldest people in the world.
But if you look at interviews with Roger Penrose, who's like 98, he's a theoretical physicist. That dude recalls everything immediately with clear, precise clarity, and it's just not missing a beat. And that dude is 98.
But that's not common.
No,
amongst the human race. For usually, the older you get, the less your memory functions well, and you start to get that cognitive decline that happens. And so the smartest people in the world are typically not the oldest people. But
typically,
given something like this, that would mean you no longer need to fear the aging process and the kind of the decline that could come with that, because there wouldn't be that decline. Instead, it would be, the older you got would be just almost an instant marker for your experiential and cognitive status, almost, because the people that were older would have so much more data
100%
to pull from. and it would have a lot bigger and more interconnected networks within their brain.
Did you mention its effect on motor skills yet? Because
I haven't. I'm not even sure I remember that part of the study, to be honest.
I thought I saw in the overview. Maybe I'm tripping. Perhaps.
I can't. I don't. Let me see. Did I put it in here?
No.
No.
Well, let's say for a second that it's reversing the age of these cells and are actually keeping them like good with a nice, good cognitive performance and the ability to change, nice, good plasticity until a very, very old age. What I think is interesting is that this could also have effect on our biology in general, and how, you know, the nerves are actually still connected and still functioning at a level as if you were still young. You could have people who are 98, 100, who have perfect bodies and aren't really aging at all in general, while have good cognitive performance, actually have good physical performance as well.
How weird would that be to as you get older, to always get hotter, like more attractive?
Please. All right, we're taking J147 now.
Imagine.
What's gonna happen?
It's like being 58 no longer means that you are.
All the fashion models are like 357, and they're like, oh, look at that. All right.
So moving on to the mechanisms of action here.
Yes.
So J147's primary mechanism of action actually is interesting. It's very, very unique. It involves the ATP, and as a result,
ATP.
mitochondrial function within the cells, which makes sense why it shows those anti-aging effects and the ability to slow down or reverse degradation.
Mitochondrial dysfunction leads to disease progression.
And mitochondrial production, or the lack of mitochondrial function, results in a decline in energy, which is a decline in the amount of resources you have to be able to spend on the different areas that need upkeep and maintenance, and as a result, over time, a degradation.
Yeah, deterioration.
And so and again, this is still active research, so it's not this stuff is not, it's
like
fully known yet, but it is
half theoretical, kind of.
They see a lot of evidence for it, but just because that they believe that is the primary mechanism doesn't necessarily mean it is the primary. Like it could be a secondary mechanism. They just haven't discovered the primary. Yeah. But that's
okay.
Right now the evidence suggests that is the the primary mechanism.
Nice. Okay.
And
that's cool. That's really cool.
Yeah. So J147 improves mitochondrial efficiency, reduces oxidative stress, like I was saying earlier, and then increases your ATP production.
Specifically ATP5A, apparently. Yes.
If for those of the audience that know,
know what that is.
Yeah.
Search it up if you don't. It's cool.
That's a valid point. One of the recent areas, actually one of the areas of neuroscience that I was most interested in studying, and one of the reasons why I started studying neuroscience, was that I wanted to understand more about neuroreceptors and the different types of neuroreceptors and what made them different and unique, and how those interactions with those neuroreceptors affected other things downstream.
What did you find?
I found that we don't know a lot of things.
Yes, that is 100% true.
But that would have to be its own series of podcasts in order to go over that. Like eventually
we'll get there.
There is a lot of. We could spend an entire podcast talking about a single neurochemical
that is
and
true.
its receptors that it interacts with.
There's like hundreds of them.
Well,
or
sometimes.
Sometimes
not all the time. There's it depends on what you're talking about. Like
yeah, you're right.
There are certain neurochemicals that have the ability to interact with certain types of neuroreceptors. Sometimes those neuroreceptors are limited to the neurochemical. Sometimes they're not, and so you have your dopamine neurochemical is limited to its dopamine receptors.
And just so I'm clear, is neurochemical synonymous with neurotransmitter? Or
yes.
Yes. Okay.
Yes.
Just making sure.
Yes.
Because I don't know the amount of neurochemicals or neurotransmitters, but I did read somewhere that there are like hundreds. But maybe it's like contextual.
Yeah, there very well could, but I'm saying like the amount of receptors that each neurochemical has the ability to interact with is not hundreds.
Oh, okay, that makes sense.
I'm not going to say that 100% because I am not that confident in my neuroscience skills yet. But
not yet. We'll get there.
But from my knowledge, based off of what I've studied so far, the coursework that I've done on the neuroreceptors, hasn't appeared to be yet.
Okay.
Okay. So going over the next one here, mechanism is that it also influences the BDNF signaling in the brain. It's if you want if there's one thing that you want to be able to influence your ability to learn and to put your brain into an optimal state for that, it is to increase your BDNF signaling.
I like to think of it as
your ability
like
to optimize that environment. You know,
I like to think of it as like a fertilizer of the brain. You know, where it allows for more growth and new production of cells.
Exactly,
that's cool.
And its mechanism of affecting things like Alzheimer's is through its anti-inflammatory properties, which are a result of its turmeric-like structure.
Yes. Eat your turmeric, just not straight. Put it on something. Unless you want to just down bottles of turmeric. Well,
so yeah,
maybe do that. I used to do that with onions. I see onions whole.
The key studies were done by the Schubert lab, where they demonstrated its potential effects in animal models for treating Alzheimer's disease. And then there was another study that was done with the fruit flies that demonstrated its effect on extending lifespan, and kind of where a lot of their understanding of its role in ATP, production came from. And then currently it's undergoing clinical trials and to evaluate its safety and
it better be safe.
Efficacy for humans.
I need this stuff.
I know.
I'm saying. Because Alzheimer's disease actually runs in my family.
Does it?
Yes. And so it's like, oh, well, if this actually has some implications, maybe it could actually help me. Like I've made sure.
You could potentially head it off before it ever, supposing that, you would have been affected by it, you could potentially, if this kind of thing were something that was found to be safe for humans, you could potentially kind of resolve the problem before it ever becomes a problem.
Which would be so awesome if that could be the case, I will say. So
I personally, I don't see you ever developing Alzheimer's. I think that your brain's too active for that. Like, it just wouldn't let it happen. It'd be like, nah.
I watch my diet, my supplements, what I take. I'm trying my best. Keep the brain active, keep the body active, keep everything nice and healthy, so that I don't have to worry about that. Because there are some people in my family who are starting to show signs of it, and it's like, my heart goes out to them. And maybe I'll send them some J147 when eventually it fixes, or when it
we could just be lab rats,
or we could take it.
Yeah.
All right.
We could do that.
I mean, I think that'd be
that
really
would be
fun.
Pretty interesting.
Yeah,
like to
100%.
do on something like where we record that process for you guys, because a lot of this stuff, at least until the clinical trials are finished and released, and that's supposing that they actually do end up going through clinical trials.
We can measure our brain states.
Exactly.
While we're doing it.
A lot of that stuff is purely, the only thing we have to go off of is anecdotal reports, and not even really effective anecdotal reports. It's more of like a text-based internet anecdotal report, of like, hey, I took this, yada yada. And obviously that presents a whole lot of problems.
Yeah.
You can, there are ways of using anecdotal reports to gauge an idea of potentially how many people have tried something, and based off of that, if a lot of people have tried something and there hasn't been any recorded cases of problems caused by it yet, then that can be a little bit of a safety measure, like for you, where you can kind of gauge the likelihood of something causing a problem. But there are a lot of things that misses, like potential long-term effects that just haven't come around yet, and other things along those lines. And so but that would be a really fun way of I guess bringing a more valuable anecdotal report to you guys with this stuff, is for us to just try it.
Just try it out.
And record the whole process. And we were already talking about potentially building an EEG.
Which we might record as well. I think we definitely should.
I think so. So we'll be looking at recording or building, and our goal is to make it a pretty dang accurate EEG. And so that would allow us to also record brainwave states, and kind of gain some data and metrics about this stuff as we take it. And hopefully give a little more information about how this stuff might work for future research. Eventually he and I would like to open our own research lab
one day
for this kind of stuff, so that we can start kind of bringing some more clarity. And I think both of us are kind of passionate about making the research happen no matter what, and despite a lot of roadblocks that typically get put in the way of that kind of thing.
We're gonna bulldoze those roadblocks, man. 100%.
Yep. So
there's a lot of them, but our brains combined, we'll be able to do it.
I'm sure of that. Yeah. So that's the overview of J147.
Yeah.
Go look at the research articles yourself if you want to.
Really cool. Put them in the link in the description.
Yeah, we can put them in the link in the description for you guys. But very, very fascinating stuff being done, especially on the kind of research front of trying to address Alzheimer's and Parkinson's and that kind of stuff, and kind of really gives you perspective on how much of our biology is dictated by our brain. and how healthy and functioning our brain is.
Yeah, 100%.
So with that said, and that kind of that research paper gone over, we need to shorten those down, that research paper section down a little bit for our next podcast, so that we can, but it provides a good segue into discussing long-term potentiation.
Yes. Oh, 100%.
And you said specifically that you had been, because I know that's something that I've wanted to talk about on the podcast for a while now. And I'm glad we didn't, because we haven't really had a successful podcast.
No, yeah.
But
there have been a lot of wasted information.
But you said there was something recently, or some stuff recently that you went over with LPP.
A little bit. So I'm taking a class on it currently. I'm only on lecture 2, so I don't know a lot. So it's kind of more so an intuitive understanding. I mean, I've done a lot of independent research on the hippocampus, So, well, what I thought was interesting in relation to J147 was that I read it here. This was on one of the research articles. Is that modulation of mitochondrial processes by J147 prevents age-associated drift of the hippocampal transcriptions, right? And so what I thought was fascinating is in relation to that, how the hippocampus, the genetic code encoded in it, and what it's pretty much just its overall functionality, what it would mean to have that working process happen over an even extended period of time at peak performance. And so I was curious about that, especially in relation to our conscious experience as well, right? Because, if you kind of see consciousness as a gradient with more complex organisms having a more integrated awareness of their experience, then when it comes to longevity of hippocampal function and processing of memories and information, and more of that being stored, what would be the implied limits then of our awareness? Because I think there's always that level of striving upwards, especially when it comes to our evolution. Obviously it's acting on random variations within the natural laws, but there is some systemic, not necessarily like teleological purpose, but a purpose implicit within the system itself, which is to maximally elongate its successful experience in its environment. And I think that a longer functionality of hippocampus at peak performance would have such a massive influence on our conscious experience, which I just find so fascinating.
Yeah.
Because, what's interesting about humans specifically is that we have kind of our genetics have given us the ability for, the biological process called imagination, right? Which is incredible in and of itself, but that it just kind of goes to show how we can kind of supersede our biology through culture and through, intersubjective interactions with the world. And that to me implies that with the sustenance of what we already have over a longer period of time, we don't necessarily need more for our body to evolve, which would be nice, right? But I think would take a much longer period of time, if not hundreds of thousands of years, even if let's say J147 is in essence like the cure to aging eventually. Let's just say that's the case. It would still take an astronomically amount of time for us to evolve to a degree that kind of makes us what people would, call, almost gods in a way, those who live forever. And, obviously we're still mere mortals. So we have the ability to die, like you said, in car crashes. But in a way, that longer integrated awareness of experience would allow us in a way to go beyond our biology, I think. And I think that's closely related to how well the hippocampus processes information and stores it over longer periods of time.
It's kind of strange when you think about it, how much of our identity as a human being he's a direct result of the hippocampus
Mm-hmm.
and the connection between the hippocampus.
You're not able to grow
right?
without it.
Like without the hippocampus, like you start losing your values, you start losing purpose, you start losing your identity of who you are. And that's one of the things that makes things like Alzheimer's so ravaging, is that for the people that are going through it, especially how that's so traumatic for them, because imagine 1 second that you remembered your whole life and all of your experiences, and then the next second you only remembered everything up until the point that you were like 10 years old. And then the next second you switch back to your adult self. And how would you reconcile the way that you had acted a second ago with the believing you were 10 years old, and the way that you interacted with your own brain because of that? How would you reconcile that with your identity as an adult, and how really disconcerting that would feel?
I think that's actually a phenomenon that happens. I think that would correlate with dissociative identity disorder, 100%, potentially.
To clarify, yes. You don't think it's phenomenal that it happens as in a good thing that it happens. You think the fact that it happens at all is a phenomena that's fascinating.
Yes. And I'm using phenomena very particularly. I'm not saying that we don't necessarily understand it neurologically, but I would say that I'm saying phenomena because dissociative identity disorder is more so of a psychological phenomena as opposed to like a very grounded neuroscientific one. But it is something that we have observed. And so it's like, okay, we don't necessarily understand the mechanisms behind it, but like we're doing with kind of more philosophical musing on the neuroscientific discussions, kind of lead us towards this understanding of those conflicting sides of our psyche, which then can induce this, phenomena that we observe called dissociative identity disorder. And I think that can happen for a multitude of reasons. I think it can be self-induced, and I think that in some ways, I know there was a movie kind of based on this. I forgot what it was called, but pretty much that multiple personalities was actually a way of combining different aspects of peak performance in certain personalities that then integrate into one being, but then express themselves as different people, which I thought was really cool. And so it's like it's a disorder as well, but in a way, it's, if done right, there could be different aspects of you that are expressed. And then,
well, I mean, if you think about, I kind of see what you're saying with that. Like if you think about, so the way that humans typically develop is we usually pick one, like we usually find one personality type that we are able to navigate really well, and it seems to work better for us. And in interacting with the world and our environment. And so that's the one that becomes the most comfortable for us. So we use that the most often and kind of build everything else off of that. However, in the case of a multi-personality disorder, if that process were something that were controlled,
there are more pathways for navigation.
Were controlled, and it was not something that was done randomly. The interesting thing that would present is the ability to navigate the world with a different outlook and set of skills depending on the situation that presented itself.
Yeah. And
so it's almost like you have several different individuals and characters. It's like you're playing a game with characters that you can choose from they each have their own skill sets and their own kind of benefits and ways of doing things. And you could just, when a situation presents itself, that you choose the best character for, the situation and the job. And that would provide a lot of really unique benefits to it. I see the issue with that being potentially the lack of communication between the personalities. And I don't know I don't know how that actually works in a real life setting because I haven't studied it.
No,
but if they didn't all use the same amygdala and hippocampus at like a shared kind of memory space where they could keep the same goals and the same memories. If they didn't, all personalities didn't share that, at least working memory, I don't know. Then it would be very difficult to actually coordinate in a cohesive, usable way that functionality.
No, I 100% agree. I mean, to some degree, the movie was cool, but
you'd lose sense of I.
Which is why I think at some point it would supersede simple personalities. I think it would kind of conglomerate into a meta-analysis of different pathways useful for that specific task navigation. And that might, and when I'm talking about personality, I just say that might express itself in ways that would never be even close to if you were doing something completely different, but that's why I think it's interesting when it comes to the hippocampus, is that, if we were able to have a longevity of integrated information, far more so than we do now, the development of those functionalities together might manifest itself as what we can see as personality, but is actually different functional navigational pathways within the brain that are interconnected, but express themselves for that specific purpose, and all conglomerate into one meta-analysis that interconnects.
Well, that's kind of already how the brain works.
It is, but I know, but it's on a scale that is far more than, you're right, it's just an extension of what we already do. But it might look similar to multiple personality disorder in that sense, if that makes sense. Potentially, but maybe you do kind of act the same throughout all of that and are just able to do that.
I think in an ideal setting in the brain, without losing the sense of I, your most optimum solution would be to find as many connections between things as possible, and have as much of your brain interconnected and the ability to communicate with each other as possible, so that you can select the right tools for any job. Ideally in that setting, your personality would play back fiddle to the actions that your processing dictated should take place. Because a lot of times, we have our personality, our natural instincts, of things that we want to do. And then given a piece of information and processing that information, we have the actions that experience has told us are going to yield the best result, which might go against what our personality wants to do.
Which is why we might need to develop a new one.
Well, I mean, it's about refining
Yeah.
your personality, less of necessarily developing a new one. But
well, I mean, personality isn't necessarily stagnant either.
No, it's not.
Yeah.
I mean,
that goes along with what you're saying, right?
Right.
Further refinement, which kind of changes yourself over time.
Exactly. Well, it's about, kind of taking the elements of your personality that you find to be helpful within your networks and in your day-to-day life, and strengthening those parts of your personality, and then weakening and reducing the effect of the less helpful parts of
separating the wheat from the chaff, not even go beyond that, where it's like, we say it's like, oh yeah, we want to separate the wheat from the chaff, but chaff is really comfortable. It's good to make beds. I will say, I like to sleep on the chaff. As you're sitting there, you kind of eat the wheat, but it's like, no, you can't. You got to discard that. You got to grow.
You can't eat that wheat. That's your bed.
Seriously,
you're eating your bed.
Bad. Very
eat your bed, but you're not gonna make it.
Don't eat your. There was this one girl on what's it called? It's like My Strange Addiction. Who had an addiction to eating mattresses.
What?
Yeah. And she was like, it's really good. She just couldn't stop eating it. And they went to the doctor and they were like, well, it's okay for now, actually. There isn't any side effects, but there could be. And she's like, it's good for me. The mattresses are good for me to eat. And so she just continued eating the mattresses. And the doctor was very concerned for her, I will say. But
all right then.
I just thought that was really funny. I remember watching that episode being like, oh, see, if you want to get into some like the weird aspects of people, then My Strange Addiction is a wonderful show to watch, I will say, because there are some weird people out there who rely on some really weird things for purpose in their life, like eating mattresses or making out with their car, different things of that nature.
Or learning a bunch of new random topics like neuroscience or something,
And I think that's the better option, personally. I think they're chilling too much on the chaff, man.
Too much of the beds.
Mm-hmm.
What are we all gonna sleep on if you go to bed?
No, seriously.
One of the in kind of relation to LTP, which is not something that is limited to the for those that don't know, it's not something that's limited to the hippocampus. It's something that happens all over the brain. And it does happen, quite a bit in the hippocampus, because that's how our memories get made, and how we store information and whatnot. Something that actually this is a bit of a diverge from the topic I was going to discuss, but something I found out recently that was interesting to me, I did not know before, was actually that I thought that our short-term memory was stored somewhere else, and our long-term memories only were stored in the hippocampus. However, it turns out that's not the case. Actually, short-term memories are stored in the hippocampus, and very briefly, but they are stored there. And long-term memory and integration and whatnot also happen in the hippocampus. Now, the one of the fascinating things is your working memory, which I think often gets this kind of portion of the brain often gets
dismissed,
overlooked, and happens in the amygdala, if I'm remembering that correctly, and is responsible for goal setting and for keeping something in your sights, so to speak. So I think they discovered this through this test, but if a monkey is kept in a cage and shown a banana on the other side of that cage, and on a banana on a plate, and then they close the lower curtain down over the cage, put a top over the plates, then bring the curtain back up. The monkey is able to reach for the container, even though it's covered with a lid, it's able to reach for the container that has the banana in it, right? That reason for that is because of the amygdala being able to keep a goal or a desire, something that has presented itself as something you want to achieve or go after. Keeps that in the amygdala in this kind of recursive regenerative loop that builds itself. And that's why oftentimes why the waiting for something oftentimes can increase that desire for it and the desire to achieve it. That signal, and again, this is from my memory of the coursework that I did on this, but that's electrical signal gradually tends to gradually increase in strength as it's being fed through this loop. And so that keeps that signal strong in your head and helps you be able to set goals and that kind of stuff.
So it modulates the importance of goals, but not necessarily the pleasure associated with it. That's up to different functions in the brain.
I think that, and I'm never going to say
100%.
100%.
Yeah.
Somebody can correct me if I'm wrong, but I think that that comes from the signal, the signal that happens as a result of that being partly as a result of that signal being released from the amygdala.
Okay.
Once your brain once you actually achieve it, and so it gets released, and as a result, kind of sends those pleasure pathways, or activates those pleasure pathways. And as a result of eventual dissipation, of the signal, in which case it wouldn't activate, anything.
Yeah.
So, I'm still learning about the ways that integrates with everything right now.
And it's probably pretty complicated.
I don't even know if we know all the ways that integrates with everything, but I do know it has a very close relationship with the cortex and the hippocampus.
What cortex? All of them?
The cortex. The
neocortex.
Right.
Okay.
Cortices. Yeah.
That makes sense.
So it almost, it would seem to almost be a necessary element to allowing the hippocampus and the cortex to work together in a functional way.
Yeah. Oh, that's fascinating. Yeah.
But anyway, back to what I was saying earlier about LTP.
Okay. LTP, long-term potentiation.
One of the things recently I I covered that I found fascinating within this coursework was the this concept of spike-dependent timing for neuron activations. And the reason I found it fascinating because this concept, we all know neurons that fire together, wire together. Everybody knows that. But this concept of spike-dependent timing is the why behind why neurons that fire together wire together.
Damn, interesting.
And it's interesting because it's something that is temporally based, meaning that without a time element to it, it doesn't work.
That makes sense.
Because what happens is the brain is able to learn what connections are helpful to each other, and as a result, grow those connections together through neurons misfiring. So they fire too early, and as a result, are not back to threshold in time to be able to be ready to fire for the next signal that comes through. And so you can imagine it kind of like a batter in baseball. The pitcher throws the ball starts coming, looks like it's coming straight at him, but they like throw a curveball and it changes the timing of it. And as a result, it takes longer to reach the plate than they thought it was going to. And so they miss too early. And as a result, they can't get the bat back in time to be able to swing again before that ball crosses them. That's kind of like spike-dependent spike-dependent timing.
That makes sense.
It is talking about the spike that happens when a neuron is activated, the electrical signal, the drop that happens as it tries to recover from it, like pulling back the bat, because it drops below threshold and then needs to come back up to threshold. And so if we have signals that are firing, one of them is enough to activate this neuron, right? So it fires. And then another signal comes through, starts going down these two pathways, and it reaches this other neuron over here and is enough to make that one fire, but it reaches this one, and because it already fired and it's down here, it can't fire again. And so that's not enough to make that one fire. So that one doesn't actually fire, but these ones over here do.
So this signal is strengthened while this one is not.
Exactly. So it learns that is something that is not useful to these connections.
Now, is this misfiring usually due to other activity within the brain, or is it simply a misfire that happens randomly? And is that how we differentiate between kind of the more complex skills that we can have?
That's a good question. From what I remember, it's a result of majority of the time it's a result of other signals being sent through. Like noise can sometimes cause, noise in the signal data can sometimes cause, misfire. How sometimes, I guess maybe a good way to describe this could be, how sometimes you've practiced something, you've got it right, you've got it right, and you can do it over and over and over again. you try it in a different context, and even though it's similar and you've done it right 100 times, by yourself, that little bit of noise can cause a different result. And so noise can cause that. You've got changes in the signal, little changes in the signal, and then also you do have I think an element where sometimes that can happen as an abnormality as a result of some other factor. And I don't think the course actually delves into that at all, like what those other factors are.
Okay.
But the majority of the time it's a result of, so, our goal then becomes, as we're learning these skills, to generalize our networks to accommodate for noise. So, we're like, these are the pathways that we normally fire. It didn't fire the way that I expected it to fire this time. And but these pathways have like kind of grown together. So as a result, maybe I need to, maybe this connection needs to be a little bit weaker, because sometimes noise can come through that. That's what it does, because like it accidentally fired when it wasn't supposed to, and as a result, the rest of it didn't fire along with the rest of the network. That connection becomes slightly weaker. It's tuning itself. It's that process of tuning itself down to accommodate for the unuseful signals that are coming through. And so that whole thing, though, is made possible through that time element of, I already fired and have this recuperation period in which I can't fire. I likely can't fire because of that dip. And for me, that's interesting, because in machine learning, that's not something it's kind of almost like a foreign concept, because everything is synchronized with each other, whether or not something does or doesn't fire, its adjustments is all like kind of synchronous processing. And there's not situations in which typically in which something doesn't fire with the next sequence because it fired with the previous sequence that went through. And so it's just a little bit of one of those interesting differences in between the brain's biology and the way the brain works, and then the way our machine learning networks work.
And maybe is that kind of what then implies why large language models are really good at specific tasks, or just AI models are really good at tasks and specific tasks, but not necessarily flexibility like a human would have. Is that kind of accurate?
There are a lot of reasons why large language models would be more or less suited to things than humans would be.
But is that an aspect of that? Since it's like long-term potentiation, brain's ability to change versus synchronicity of, high resolution task functionality.
It's hard to really say one way or the other, because generally speaking, the outcomes are kind of similar.
Yeah.
But the difference is that the training process might be different. Because our brains are constantly, in some form or another, training and learning. Like even if it's minuscule amounts, they're still doing it. Whereas with networks, we train them and then stop their training.
Yeah.
And keep the model as is, and in order to be able to use it for specific things. And so most of the time, models aren't constantly adapting and being trained. There are exceptions, like we have I think Gemini has a Google Gemini's model has a reinforcement learning model backing it that will continually train it on useful data.
Oh, that's cool.
And so there are kind of exceptions to that, but it's just so different in the way that it functions, and it's as a result of the hardware differences, between the brain and the computing power that we currently have, like CPUs and GPUs, like we rely on being able to do calculations, asynchronous calculations synchronously, which may sound like I'm saying opposite things, but the doing a lot of different calculations at the same time that go together. So like with the GPU, one of the reasons why GPUs are often used for machine learning is that they allow for us to run calculations on the different neurons weights and whatnot. They allow us to run those calculations all at the same time. So we run multiple calculations for these single neurons and calculate the results of these matrices, and whereas if you were doing it with like a CPU or something like that, those would be more synchronous, meaning that I would have to do instead of being able to do all the neurons in a layer, or like 50 or 100 neurons in the layer once, those calculations, I would instead have to do like calculation for neuron 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. And like kind of
step by step,
it becomes less wide, less of a calculation that's done like kind of wide and all at once, and more of a like rapid fire, like one after the other calculation. That's actually fun fact. That's one of the big differences between CPUs and GPUs, is that CPUs are designed for these kind of process dependent tasks, like creating. That's why you have threads, like CPU threads and whatnot. We need to run programs on our machine, and those programs typically kind of run in a more or less synchronous fashion. And so CPUs are designed for that architecture where I need to have Chrome running over here, and I need to have a notepad running over here. I need to have this other application running. And so like having all of these processes that are all like running their own things. Yeah.
And that's governed by the GPU.
That's the CPU.
That's the CPU.
That's the CPU. And that's why a better CPU is better for work-related problems, because usually work-related problems are involve running a lot of applications and that kind of stuff when we're talking about typical work environment. And that's why games and graphics and 3D modeling and whatnot, that's why GPUs work better for those applications, because those require a lot of calculations at one time. And though, they're not going to be as fast as those calculations aren't going to be as fast, they will necessarily, I'm not going to make that blanket statement, but they're not necessarily going to be as fast as the CPU. They will be able to be all done at the same time and delivered. And so, we've got with graphics, you've got a lot of calculations that have to be made with these, the pixels and the movements and animations, all this kind of stuff. And so being able to calculate that in a kind of asynchronous manner, meaning done all at one time, then that allows for a better delivery for the data format, that they're needing. And so
fascinating.
Yeah.
More I guess.
If we really wanted our machine learning models and architecture to resemble more of the human brain, if we wanted to redesign it that way, we would have to really start looking at our CPUs, not our GPUs. Like, we'd have to start developing our CPUs to be able to better function and handle those.
Can you see any relevance as to why we would need to model them a little more like human brains?
Yeah, I can. For task-specific work, like developing a model for a specific task, our GPU architecture works well. Like it's something that is functional and somewhat efficient. But for contexts like unsupervised learning, and unsupervised meaning you don't really control the data that goes into it. For contexts like that, and for making models more efficient at what they do, I think modeling it more after the way the human brain works would be better, because that would give us clear pathways and calculations that only happened when they needed to.
Yeah.
And not just because they were all lumped together in the same layer.
I see. Yeah.
Because when we generalize these things, we create a lot of unnecessary work that doesn't necessarily need to happen.
We want to refine that. Just like our brains do.
Exactly. So yeah, it's one of those problems that I've been trying to work through with machine learning and see if there's a good solution towards. But
cool if you could find one.
Yeah. It's also the inspiration behind learning more about the human brain and the hippocampus and how LTP works and that kind of stuff.
Yeah. Let me know what you find, because I'm trying to look into that stuff too,
Yeah.
Gee boy. But it sucks because I have to do a lot of school, so it's like I have all this useless information that I have to remember for my classes.
Oh my gosh, I know. Don't even get me started on that.
But I want my degree. Once I get done with my bachelor's, I'm like, okay, great. Now I can fully focus on what I actually want to do. And then the classes actually get good.
Unfortunate that the degrees are so highly regarded when they require so much learning of useless information.
I mean, I'm not going to remember any of it once I get my final grade. It's like, bam, gone. Away from my memory. I don't need you anymore. Get out of my headspace, Yeah. I mean, you kind of can do that a little bit, So thankfully, it is not going to take up too much space in my brain in the long term, just in the short term, So
Yeah.
should all work out hopefully eventually.
Just retrain those pathways eventually and get that information out of there. Let's see if I can find some of my notes on the. There we go.
Ooh.
There was a recent development from Google. A new quantum computing chip called Willow.
Oh, I've heard of Willow. Yes, I don't know a lot about it, but
I was watching the announcement on it, and I was like, this is really cool. I don't really know why it's cool,
but it is,
because I don't know enough about quantum computing to understand why what he's saying here is relevant, which kind of spurned that
curiosity
to research and figure out what's enough about quantum computing to be able to understand what they're talking about there. And it is impressive, this step that they made, and it's a step in the right direction. It's not, and I was hoping it was going to be a step towards bringing consumer level quantum computing.
Dude, that would be great. If our
But
laptops could have quantum computing inside them,
right,
run a lot faster. Maybe I could actually use the webcam. Yeah.
Oh my God.
Ugh.
Yeah. Unfortunately, well, I mean, it could be argued that it is a step in that direction, but it's just not a very big one. It's a it was more of a working through some of the kinks of the quantum computing technology as as in its potential for being utilized as a hardware. And specifically, they were talking about random circuit sampling, which I was not sure what that actually was, because I've not looked into quantum computing before, and that was term that's used for testing things in quantum computing. And so that's kind of what spawned. It's what spawned a lot of the research that kind of followed thereafter. But basically, what they were saying was that that there was a large improvement in its random circuit sampling outcome, and so in order to understand why that was relevant and helpful, I needed to kind of understand a little more about what that was.
So what'd you find?
That it is the random circuit sampling. It's interesting because random circuit sampling is essentially a test let me put it this way, is a way to create a test for a quantum computing circuit. Like, it is able to basically it's kind of a randomly generated circuit or list of gated operations that get applied to a qubit in order to prompt a response from it. And so
are the responses of these randomly generated circuits compared and then refined past that point?
So the responses are measured afterwards.
Okay.
And
those measurements are used as data to then continue furthering quantum computing.
And let's see if I can find exactly the the part on this that I wrote down. It's kind of like benchmarking its efficiency, almost like testing its ability to handle different circuits or inputs, and it's and by using random circuit sampling, they're able to it helps provide proof of concept for quantum computing, and as well as like the benchmark for which its computations can be measured and then assessed. And so I was trying to understand qubits.
What are qubits?
I was trying to understand this RCS, random circuit sampling, and how those like related to each other, and how that process even works. Like what does that look like? And throughout this kind of like this and quantum computing was one of those things that's really difficult for us to get our heads around as humans, because, and I kind of delve into this a little later, but it's because of how it's almost like trying to imagine like 4 dimensions of space.
Yeah.
That's essentially kind of how it feels. And so I came up with, and throughout this process of asking questions about specific terms that I was coming across, and refining my knowledge of like how that stuff actually plays out. And again, this is pretty new for me, so bear with me here. But I was able to come up with a really, really good analogy to help understand this process, and this process of RCS and quantum computing using qubits.
Qubits are quantum bits. So they aren't just ones and zeros, but actually exist at a superposition of states.
Right.
Okay.
And that's easy.
How does that work in computing?
That's easy enough to say, but when you actually delve into,
I have no clue what that means.
You don't. that was me. When you delve into like the mechanics of trying to imagine, okay, like how would that actually be used in this process? How could you possibly, even work with that, and what does that mean when something is in this superposition, in this relation to its output state, that it ends up in, like how does those two like correlate? And so that's what I was trying to figure out, and in order to kind of try and understand this process.
Yeah.
And I came up with a really accurate analogy for it that really helped me visualize what is actually happening here.
Yeah.
And now it's difficult for me to like think of it outside of this analogy context, because
it's too good.
It just works, so well. Let's see if I can find it here. Give me 1 second. Almost there. Yeah. Okay. Here we go. So I wrote this down because this was the way that my brain was flowing. in a state in which it was making sense of things very easily. And so I didn't want to lose it. So the initial operation was a sequence of gates, which is what RCS is. Mm-hmm. It's the random circuit sampling. It's a randomly generated circuit or sequence of gates that's applied to a qubit. But the initial operation, that sequence of gates applied to the qubit, is like blindly filling a bag with red and blue marbles. And the measurement of the output of that operation is like blindly taking a marble out of that bag. Until you take the marble out of the bag, you won't know which marble you're going to get. But there still exists within the bag a probability distribution that weights the likelihood of pulling out a marble of one color or the other. Mm-hmm. Once we reach into the bag and pull out that marble, we see the outcome of that probability distribution. Mm. So, what that means is with random circuit sampling, we randomly fill a bag with red and blue marbles. There's an unknown amount of marbles in this bag. We can't see into the bag, right? So until we choose a marble out of the bag, we won't know what we're going to get or the likelihood of what we're going to get there.
Wouldn't it be 50-50?
No. Because it's a randomly filled bag of marbles. So there could be 90 red, 10 blue in the bag. There could be 1 red, 90 blue, or 99 blue, or there could be, 50-50. And your probability distribution before reaching into the bag is going to be the ratio, of the different colors mm-hmm. that are within the bag. So we filled it randomly. We don't know what's inside. So there is, until we reach in the bag, we'll have no idea what that outcome. It could be anything, And by reaching into the bag and pulling out a marble, we now know what the outcome of whatever probability distribution was in the bag is. We know the outcome now because I picked a color. And so that is similar to what happens with quantum computing.
That makes sense.
It has a sequence of operations that causes a unknown outcome on this qubit. It gets sent into this superposition state, mm-hmm. right? Meaning that it has a probability distribution that is unknown to us, that it could land in any of its two states, Mm-hmm. So it can either be true or false, right? The outcome, once we measure it, it's either true or false, right? When it gets sent into the superposition, it gets a probability distribution that is going to be either true or false. We can't measure that. We don't know what that probability distribution is. And it is only by taking a measurement of that we can know the outcome of the probability distribution. Mm-hmm. And so, one of the difficult things for people to wrap their heads around, besides the probability distribution, which is not a term that people are generally using in their day-to-day life, but it just means the weight of the likelihood of something happening, like versus other mm-hmm. things happening. So like kind of the weight, it's like, oh, it's if I'm a coin and I'm leaning this way and I'm spinning, it's way more likely that I'm going to fall on this side, than,
Yes.
that's like the probability. And then the other part is that is wrapping their heads around the fact that when it gets sent into that superposition, it actually exists in all possible states at once. It's in every conceivable outcome. And so we would often term that concept of being in a superposition in all your possible states. The way that we would talk about that in our day-to-day life is we would actually say the opposite of that, which is interesting. We would say we're in none of the states. For instance, if you consider a coin that is flicked and spun on a table, it's spinning, it's got a certain lean and bends to a certain wobble, so it's got its probability, that it's going to, land in in one state, but it currently is kind of in both of its states. It's a little bit on one side and a little bit on its other side. And it's like, for instance, if we look at it like a, pie, it would be, if it was at this particular time, if it was like leaning this way, it might be 100 or 200 degrees, one way, and then 160 degrees the other way, giving it, giving it a certain amount of each state that it's in, right?
Yeah.
So that can kind of be thought of like it's superposition where it exists in all states. It does exist in all states, and the states, that are there, determine its probability distribution. We don't know any of that because we're not able to actually measure it, because measuring it causes,
It would just be classical.
well,
At that point,
measuring it causes it to choose a state. It's the same concept as in order to actually like get a actually a better analogy for this one would be using the spinning coin. In order to be able to determine what side it lands on, you have to stop it from spinning. Put your hand down it, stop it from spinning. That forces it to choose a state, and so now it's on one side or the other. So that is to further kind of refine and clarify this analogy and how it relates to quantum computing, or just quantum mechanics in general. There's another element that we need to add to it, and that is the fact that measuring can actually change the probability distribution of it landing in any one state.
Because doesn't it disrupt quantum coherence?
Yeah, it collapses wave function. Yeah. And so
it's very delicate.
The bag analogy still works there, because if we consider the bag of marble that's been randomly filled with marbles, we don't know what's inside there, how many of what is inside there, but it does have a distribution of probabilities. Before you reach your hand in the bag, it is pretty much, equally likely to pick any of the marbles within the bag, right? Once we put our hand in the bag, as we start inserting it below the depth of the marbles, further and further down, that probability distribution changes because of how deep we are into the bag. Now, the fact that we've stuck our hand into the bag has further refined that probability distribution of like, okay, well, now it's less likely that they're going to pick up one. They're going to pick a marble from the top because their hand is underneath the top. So the probability distribution as a result of the measurement changes.
Yeah.
And so
Isn't that kind of along the lines of quantum entanglement, if I'm not mistaken, where that measurement would then affect the probability of other
I don't
bits
know
of
enough about
information?
quantum entanglement to be able to tell you that.
Okay, well, we can look at it later.
I just finished understanding qubits, so give me a little break here.
No, yeah, you're good. You're good. Anyways, continue.
Yeah, no, but that's basically it. And then once we actually pick a marble, pull it out of the bag, look at it, we know what the outcome was.
Mhm.
That's like what it's doing here with the qubits and the
That is
quantum
so-
mechanic principles. Yeah.
Now, does this allow simply for more calculations to happen as opposed to like classical computers? Like, is it more of something we already have or something fundamentally different computationally?
It is something. I would say it's more along the lines of something completely different computationally. In their current, it's almost like, so one of the other things that that I wrote down here, and I think this actually is relevant to what you were just saying, so bear with me. Just see if I can find where that was. Here, but I was basically here we go. Okay. It's difficult for us to visualize and even incorporate entirely accurately what's happening into an analogy for it, mainly because in our perceivable existence, we have certain linear time constraints.
So it can process multiple things simultaneously?
Well, just give me a second.
Sorry.
I'm
excited.
I.e., at any given point in time, any given object is already in one state or another. For us, that's the way that we live. And thus has a calculable outcome because the states are already set at that given point in time.
Yeah.
So it's in essence like we live inside the qubit measurement. Like we are within the measurement environment, and it's difficult to visualize things from outside the context of a specific measured point in time. Qubits, on the other hand, exist outside of that linear measurement until they're measured. It's almost as if time has a second dimension to it for qubits, in which they exist in all their possible states. And it's like we're inside a measurement. We're trying to measure something outside of it by pulling it into the measurement, but like pulling it in, is like only a piece of it, And so the real answer, like to your question, because that is like, it's completely different because we're not using something that is based on physical states that things are in. That's how logical circuits and processors work. It works through states and logic gates and whatnot. And so because we're not relying on that, it's a completely different process. And it's almost like living in a 2D world versus living in a 3D world. Like it adds a whole,
so it enhances the depth of inferences that
and
can
information
be
that can be and allows for not only faster computations but way more complex. Like right now we're limited by the kind of calculations we can make because of the fact that we're bound to physical hardware, logic gates, and states. So we have to be able to account for all the states that we might want to process with.
Yeah.
And if we want to make like a number, like a really long number, and perform calculations on it, that is all stuff that has to be computed on a state by state level within the within our hardware. And so that's why we have things like 16-bit numbers and whatnot in computing, 32-bit, 64-bit operating systems, that kind of stuff. Like, so what a qubit does, imagine that, but without the 64-bit, an infinite bit.
Okay.
So we no longer have a limit to our bit size that we can use.
Yeah.
It's kind of like that, because what qubit does is it doesn't, we're not constrained by predefined states or on or off flip switches. It's a distribution. So instead of being 0 or 1, it's 0 infinity in between. Like
wow.
Yeah.
That's really cool. Okay, that actually does answer my question. Okay, now I think I kind of at least simply understand intuitively what quantum computers do.
Yeah.
Now, which is huge if that would be implemented on a entire societal level.
No, it completely changed
everything,
the way that we live life, because most people don't realize, but programmers and machine learning engineers are faced day to day with the fact that our society is super limited by our hardware technology constraints. Like the amount of things that we could do if we had the hardware to do it is, it would bring the next age in human development. It's like we just reached the information age.
You get to, like,
if you wanted to, you could even call the age of AI an age, although it's kind of within the information age.
Yeah.
But the making consumer level quantum computing that could be practically used would bring the next, and likely one of the final stages of human technology development. And would infinitely expand our ability to study the universe, heal people. Now we could develop machines that, for things like performing surgery, that would be able to make more precise and infinitely faster calculations than any human could. So that would open up a whole new world for medical development and what was possible with medical technology now.
Yeah.
Like, can you actively prevent somebody's brain from dying now? Like, can you stimulate, areas or prevent issues almost at the same, or stop issues almost at the same instant that they happen?
Yeah.
So it's an exciting era. Like anything that has huge impact and implications, it's it comes with a little bit of how could this go horribly wrong, kind of feelings within it. But
can't help but be excited.
You can't help. No, it's like whatever's gonna happen, it's gonna be big.
Exactly.
Yeah, I mean, I just hope that we that I'm able to live long enough, and that the human race
with J147
able to live long enough that's to see like that consumerized and
that'd be awesome. I mean, it's really hard to predict the expected rate of technological advancement. I would say that it's possible that we'll get to somewhat of that state potentially within 50 years. Now, I'm curious as to see how they're going to overcome the delicacy of quantum systems and coherence, and if that would be able to be overcome on a consumer level. I don't think we'll get it in our laptops anytime soon. That's for sure. But maybe in a computer chip in our brain.
Yeah, I mean, that's a really
where we interface with our thoughts instead of with exterior technological machines implemented straight into our interface with reality.
Right. That's actually a good example of how quantum computing could change our lives. Is that you're it's difficult to predict the rate of technological development. That kind of stuff, that level of complexity, even the future state of humanity and future events could be accurately predicted with quantum computing, because we now have the ability to process so much more information that we can feed it all the information that we think might be relevant and not worry about the computational limits of that kind of thing. And so right now our models are very, very constrained, because we're we gotta do so much picking and choosing of the information we feed it and the features within that information in order to try and make sure that these things are accurate without being completely unfeasible to train. But those kind of really complex predictions, even the potential life paths for people, what their life will look like from beginning to end.
If there is an end.
Right. Those kind of things could be predicted with quantum computing if you're able to get the necessary data for it.
Yeah. That is interesting. Definitely interesting, I will say. And that also kind of comes, with implications of, will then the illusion of free will dissipate by that point?
That's a good question, because it almost forces you to confront that fact that none of your actions are really your own on that level. Like you are always going to do what it was that you did because of the circumstances you were dealt.
Like seriously, like what if we do implement within our conscious awareness a quantum interface? I
think that could kill our brains.
Potentially, but maybe
too
not.
much data, too much information.
Potentially, but
see, it's interesting too because with quantum computing, it then begs the question: if we made an AI, if we were able to recreate the human brain using quantum computing, which would require us that we understand the human brain a whole lot more than we do, but if we were able to recreate the human brain using quantum computing as the processing elements for it, we would essentially be creating a brain that was infinitely smarter than ours.
Infinitely.
Like,
how can I get that brain in my skull?
Right.
That's the question.
Well, I feel like as much as I would love for it not to be the case, I feel like if you were to take your brain's state, say you were able to map out the state of your neurons in your brain, and you were to transfer that over to a quantum brain in the exact same, kind of amount of neurons and like the states and whatnot that they were in, transfer that over to a quantum brain. First off, I feel like you would stop being able to interact with the rest of the world because you'd be seeing things in a completely different reality. Like your brain would be moving so fast that like everyone else would probably feel like they were in slow motion or worse. Like, and then on top of that, I feel like depending on how it was implemented, you might not even end up as the same person because
definitely not. You would be a completely different person.
Because the rate at which your brain would process information and grow and develop and change would require and also prompt, but require the a personality change or changes. Like you might go through several iterations of personalities, like just because of the experiences that the amount of experiences that you're processing.
No, 100%. So maybe not, but then again,
that would be weird because it'd be like you were a quantum being limited by non-quantum sensors. Like your brain would be like, it'd be like your brain was it's like your brain was in a quantum, another dimension, whereas
while I was still biologically
limited by
the world,
the 3 dimensions that were in 1 dimension of time that we're in.
That's fascinating.
I don't know if that would be.
What would happen?
I don't know if that would be comfortable.
I feel like, in a way, you might almost be just stuck in time, actually.
Like, how would that even work? Because your brain,
just let evolution take its place.
Your brain wouldn't be limited by time, but your body would be.
Okay. So what I'm hearing is take my brain, put it in some like gel and let it sit there and do its thing for eternity.
You might as well at that point.
Yeah.
I don't think your brain's going to be able to make much use of your body at that point.
Or maybe, I just kind of, once we stop with this whole aging thing, I let evolution take its course and let it, integrate into each other for quantum experience unlike anything else.
Don't know if it works that way, but we could try.
I mean, I'll be the lab rat for that.
If there's one thing that you can rely on us to do here, is to be lab rats.
100%.
We will
quantumize our brain.
do whatever is necessary to bring more information to you guys. And with that, I think that is a good
stopping
place.
Awesome.
So I hope you guys are as excited as we are to have a podcast with audio.
Yes, we're so hyped. It's going to be wonderful.
And we will be in probably about a month or so. We'll be changing locations a little bit, and but until then, we still should be delivering things week by week, podcasts week by week, and we'll look into perhaps also doing some stuff in between, like our research logs and whatnot.
Yep.
For some of this stuff.
100%.
But thank you guys for sticking with us.
Thank you.
And hope you guys enjoyed it. And if there's any papers or anything you guys want to see us cover, sure to let us know.
We'll do a deep analysis of it. 100%.
Well, we will talk to you guys next week for sure, and maybe sometime before that.
Yes. See you guys later.